Welcome to the lecture on solute redistribution during solidification. So, many a times we come across the terms known as chemical inhomogeneities. So, especially during the weld microstructure. So, pertaining to the discussion on solidification topic, we will talk about the solute redistribution issues which occur during the solidification, because when a liquid of certain composition, certain solute composition that solidifies, then basically it is all by the by the process of nucleation of solid, and then there will be nucleation, and then further there will be growth. So, you will have solid which is coming out. Seldom it is when you are talking about the alloys with freezing range. In those cases the solid as well as the liquid composition, they will be changing, and that leads to the cases of homogeneities depending upon many factors. So, this in this lecture we are going to discuss about those issues and have some idea about them. So, when a liquid of uniform composition solidifies, the resultant solid is seldom uniform in composition, because you will have, we will discuss that in case of alloys when we talk. So, in those cases you have the solid which is coming out, it will have different composition than the liquid. So, the solute atoms in the liquid are redistributed during the solidification, and this redistribution of the solute that will be depending upon the phase diagram, diffusion under cooling, fluid flow, and so on. So, these are the factors basically which basically define that how there will be the redistribution of the solute. So, coming to the about the we have already talked about the phase diagram, and what we have seen that when we see the solidification of certain binary alloys. Now, in this case, as we know that when you have the solidification, so if suppose you have the melt of this composition. So, this is your solute concentration. So, if your melt is having this concentration C naught. Now, as you know that when you so this temperature is the Tm. Now, when you come to this temperature, this is the liquidus temperature, and this temperature will be known as the TL for this composition. Now, what happens that at this temperature the solid which is formed. So, this is solid concentration in this direction, and this is basically the temperature T. So, so at this point at this liquidus point, your at this point the solid which will be formed, it will have the composition, and this is defined as the concentration of the solid. So, this is known as CS. Now, at this point the liquid is having that concentration C naught. Now, as you go further down, so suppose you are coming to any temperature T. So, if you talk about this point which is having the temperature T. Now, at this point, as you know, the CS which was here, now at this point this will be your CS. This will be the concentration of the solute, solid having solute in the solid. So, basically this CS will be varying along this line. So, you can remove this. So, if you talk about a particular temperature at temperature T, at this T temperature the solid which is crystallized out, it will have the concentration CS, and similarly you will have you are coming to this line. So, if you are having this horizontal line drawn from here. So, as we have already seen that this composition is known as Cl. So, Cl is C naught at T equal to TL, or however, as we come down. So, this Cl will go on following along this line. So, this will be your Cl. So, this is your solidus line, and this is known as the liquidus line. So, the concentration solid, so it will be following concentration of the solid which is crystallized, it will follow this line, and of the liquid it will follow this line. Now, if you talk about a term, so there is a term known as the equilibrium partition ratio. So, the equilibrium partition ratio so this is defined by the ratio of Cs to Cl. So, this K will be Cs to Cl. Now, as you know, in this case the Cs is lesser than Cl. So, in such cases your K value will be smaller and it will be less than 1. Now, if you talk about another kind of phase diagram where the phase diagram goes like this. Now, in this case what we see that if you come to any composition C naught. So, now in this case again you have the temperature T is going like this, and this is your solute concentration. So, in this case as you come down, so if you talk about at any temperature T, so this will be your Tm, and at any temperature T, so if you talk about T, so this is your solidus line and this is your liquidus line. So, in this case you will have Cs touching to this point. So, this will be corresponding to Cs and this will be corresponding to Cl. Now, what we see in this case is Cs is having a larger value than Cl. So, solid which is crystallizing out, it will have the solute concentration more than what the liquid has, and it continues to grow. As we come down, it continues to fall down basically in this case. So, it will follow. So, as you decrease the temperature, this Cs value as well as Cl value, they both will be decreasing with time. Here, whereas in this case Cs and Cl both increase with time. But if in this case if you talk about the equilibrium partition ratio Cs by Cl, so in this case K is more than 1. So, as you see that there are two cases, one is Cs is less than 1 and another is Cs is more than 1. So, if you define the slope of this liquidus line as ml. So, if ml is the slope of liquidus line, in that case you can because slope is less than 1 in one case, in this case it is less than 1 because this angle theta is more than 90, and in this case slope is more than 1, more than it is positive, one is positive and one is negative. So, in that case you can have the expression for the temperature T on the liquidus line. So, if you the temperature T in the liquidus line will be Tm plus ml into Cl. So, that is how you can have the calculation of the T in any case. Now, we will talk about the different cases when you have the difference of diffusion. So, this was related to the phase diagram, and also we defined the equilibrium partition ratio, which basically will be talking about the ratio of CS and CL. Now, we will see that depending upon the different diffusion rates in the solid and in the liquid, how different cases arise. So, we will talk about a case in which there is complete diffusion in solid and liquid. So, if there is a case of complete diffusion in solid and liquid, so basically that makes you to understand that in these cases you will have the solid or liquid of uniform composition you will be getting. If there will be complete diffusion in solid and liquid, because there will be redistribution of the atoms at the interface, solute which is coming out, it will have lesser So, once if you come to the lower temperature, then all these solid phases which are there, so they basically will be redistributing the atoms. So, in those cases how these how you get these how it looks like, the how can you show it this solute redistribution in those cases. So, suppose you are taking for a case. So, first of all this will happen in these cases you will have the condition. So, in the case of the dissolution in the solute or solute diffusion. So, for that basically in the solid state the condition will be ds into T should be more than L square. So, basically ds will be the diffusion coefficient of the solute in solid. So, and similarly you will have the diffusion coefficient of the liquid also. So, in liquid case you should have again dl into T, it should be again more than L square. So, as L is the initial length of the liquid in this case. So, these are the conditions so these this is diffusion rate, this is time. So, basically that should be quite higher than this distance through which it has to diffuse. So, these are the conditions, and certainly depending upon the dl and ds values the diffusion rate will vary. Now, the thing is that when you have a case of complete solid diffusion in solid and liquid. So, in that case your how it varies. So, suppose as you have seen you have going like this will be your solute concentration. So, this line on the x axis you have solute concentration, and this way you have the temperature. Now, as you know that in this case as that if suppose you are coming to this C naught concentration. Now, at this temperature T, so so this will be your TL, that is your liquidus temperature, this is your at a defined temperature T, and now this will be so at this point where it is touching you will have this is as the CS, and similarly you will have so this is your CL. So, it will be Kc naught. So, this will be basically Kc naught. So, Cs will be nothing but Kc naught, and this will be Cl. So, that will be C naught by K. In this case basically the K value is less than 1. So, that is why this will be C naught by K. Now, in this case so as you see that this is your K is less than 1, and this is your initial melt composition, that is C naught. Now, what happens that in such cases, if you look at the Cl and Cs, so what you see that if you draw, so this line, so this will be C naught, and this C naught, which is the coming for the liquid. So this C naught basically, so from here this line will move and it will go up to C naught by K. So this is for the Cl value. As you know that this for liquid, this value will be moving, this is C naught. So at TL your this C naught is Cl, and then so here you have this C naught, and then it will be so it will be moving, and this will be coming to this C naught by K. So ultimately your this value is C naught by K. So you are coming finally to C naught by K. So this will be your C naught by K. For the liquid, it starts from C naught and goes to C naught by K. For the solid, it will be starting from Cs, and then it will be so this Cs line will go and ultimately it will come up to C naught. So if this becomes C naught, then for Cs, so this line basically will be coming as Cs, and here from you will have this line moving up to, so it will be touching finally this line. So your this will be your Cs, that is for the solid, and this will be since it is also depending upon the solute concentration only. So this is CLFS. So this will be your if you look at in this case, this is this axis is fraction of solid, and as the fraction of solid varies, it varies from this value, that is this is K C naught. So this is nothing but this is K C naught, and this is K C naught to C naught, and then C naught by K it's going. Now if you look at the total volume of material which is formed in such cases, so if you try to draw this graph again, so what is happening is that if suppose this is the solid form, so some part is this is solid and this is your liquid, which is liquid part. Now as you have seen that for the solid you will have you will have Cl. So this is your Cs, and from Cs it will go up to C naught, and similarly, so this is your C naught, and for the liquid it will be moving. So it will be going from here to further to this value. So this part is the fraction of solid, and this will be the fraction of liquid. So fraction of liquid is nothing but the 1 minus fraction of solid. So basically Fs plus Fl that is equal to 1. So you will have the if you look at the solid part, it will be this part will be solid, and you will have this part as the liquid, and your solid at the end will have the composition C naught. So you will have the uniform composition C naught all throughout. Now if you have if you look at the hatched areas, now you have CSFS and CLFL. Now these are the amount of solute. So they are the respective amount of solute. There will be amount of solute in solid and liquid. So these show amount of solute in solid and liquid. Now if you see the so Fs and Fl, we know that this is fraction of solid and the liquid. Now, the area, that is so you will have uniform composition C naught. So, C naught Fs plus Fl. So, this will be the amount of solute in liquid before solidification. So, if you equate, you will have CSFS plus CLFL, that will be C naught into Fs plus Fl. So, Fs plus Fl is 1. So, you will have, that is known as C naught. So, if you substitute Fs equal to 1 minus Fl, so in that case you can have the lever rule. So, that is formed, that is Fl is C naught minus Cs divided by Cl minus Cs, that is the equilibrium lever rule which is obtained. Similarly, you get the Fs, and Fs you get as Cl minus C naught by Cl minus Cs. So, this is what you get in the case of complete diffusion in solid and liquid. And you also get the composition of liquid. You can have the expression for the composition of liquid Cl, and that can be formed found out by C naught by Fl plus K into 1 minus Fl. So, depending upon the value of K, the equilibrium partition ratio, in terms of that and fraction of liquid, and for the particular composition, you can have the concentration of that liquid portion that can be found out, and they basically help us in predicting many things, like how that Cl will be changing, based on that how the liquidus temperature line will be changing, because as we know that as there is decrease in the temperature, in those cases you will have the change in the liquidus temperature line. So, based on that there will be few more events happen, a few more phenomena occurs, like what we will discuss in our coming lectures. So, because of the problem in the solute redistribution. So, this is for those cases where you have complete diffusion in solid and the liquid. Now, if you may have a case where you will have the diffusion in the liquid is there, but diffusion in the solid is not complete. So, you do not have the diffusion in solid, but you have the complete diffusion in liquid. So, you may have the case of no solid diffusion, but you have a complete liquid diffusion. Now, in these cases basically for them the condition is that if the condition is such that your dSt is quite less than L square, if the this distance is quite larger, in that case it means the diffusion in the case of solid is quite small, whereas the dLt, so this is quite larger than L squares. In such cases when your diffusion in that solid case is solid state is quite small. So, in those cases such conditions are faced, and how so what will happen that you will have the equilibrium only case only on the interface, because inside the solid there is no redistribution, there is diffusion is not so fast. So, you do not have the uniform composition in the case of solid. So, in this case solute cannot diffuse back into the solute into the solid, and so it will reject, it will be rejecting these solute, and that has to go into the liquid. So, in fact, for the liquid, basically the concentration in the liquid portion, the concentration in the liquid of the solute will go on increasing, and since from this liquid only the solid has to come out. So, since its concentration will go on increasing, so the solid which is formed later on, it will have its concentration will also go on increasing. So that way you do not have uniform composition of this solid all which is formed. So, at the end of the solidification, if you look at the solid phase, you do not have the uniform basically composition of solute. So, if you look at its case, so what happens that if you see this is the case. Now, in this case again we are coming to this concentration as C naught, and then at this is the temperature T. So, you will have this as the line CS, and so this will be so it will be nothing but Kc naught, and when it is drawn horizontally and it is touching this liquidus line, so it will be C naught by K. Now, as we discussed that in these cases your these concentration, if you look at you have complete liquids diffusion in the liquid, whereas no such case in the case of solid. So, if you draw, so your this CS will be coming, and this is your case C naught. So, this is your case C naught, and this is your C naught. So, C naught is mapped here. Now, this will be CL. So, this CL basically it will be moving to very large value than C naught by K, because of the because of the very high value of diffusion in case of liquid, and there is very poor value in the case of solid. So, your CLFS line, this will be going quite more than this. So, you will have this C naught by K value is here, but it goes quite past this, and since this liquid only, from this only, because it has larger concentration of solute. So, from there only the solid is formed. So, solid also in the later part it will also go and it will also move, and it will be reaching also, it will have the larger concentration value towards the end. So, this way if you look at the fraction of solid and the liquid. So, in this case, if suppose we talk about the solid and liquid formed. So, what happens that you will have the this is your CS line, and this is basically, if you talk about in the bottom, if you talk about this as the solid portion. So, this is your solid. Now, this is so here also it is decreasing and coming to CS, suppose at this is instant. So, your this is your this will be your hatched line, that is your solid, and then so and this side you will have the liquid. So, here you will have larger concentration. So, this will be your CL, and in between you have C naught. So, now because of that you will have this is your liquid part. So, now in this case you will have the movement from here, it goes, and for the liquid it will be moving from here, and then you will have larger concentration at this point, and this will go further. So, that is what we have seen. So, if you talk about the cases in such case, so what happens that this is your Fs. So, you will have Fs on this side. So, basically you will have the sum of these hatched area, they will be amount of solute in the liquid before solidification. So, what happens that if you look at the further, this is what we see, that you will have this area going, and from here, so you will have the increase in this zone. So, and on this side you will have increase in this Fs. So, this distance is taken as dFs, and this is taken as dCl. So, so in those cases what we take is that this hazard area will be equal to the amount of solute in that before the solidification. So, hazard area 1 will be equal to 2. So, based on that, so you will have one is increase in this area and another is increase in this area. So, you will have C naught coming up here, then you will have K C naught here. This is your this is your CS. So, that way same expression comes out, and this is your CL. So, then in that case if you equate, so what we get in these cases, if you try to find the expression, so your expression becomes CL minus CS into dFs. So, that will be equal to 1 minus Fs into dCl. So, basically this increase in area should be equated to this increase in area. So, that will be your so if you equate that, so dFs, and this will be CL minus CS. So, that this area will be equal to dCl into 1 minus Fs, because this will be your FL. So, that is how. Now, in this case again, if CS is taken as KCl, and if you integrate these equations, CL equal to C naught at Fs equal to 0. So, in those cases what you get is the equation which you get is CS will be, you are getting as CS equal to K C naught into 1 minus Fs raised to the power K minus 1, or you also get CL as C naught into FL raised to the power K minus 1. So, these two equations which you are getting to find this CS and CL, they are known as the shell equation. So, these are the shell equation. So, this is the solute redistribution equation. They are representing the solute segregation when you have the no proper solid diffusion and you have complete liquid diffusion, and from here you can find the values, like you may have the expression for FL as CL by C naught raised to the power 1 by K minus 1, or you can also write C naught by CL raised to the power 1 by 1 minus K. And then in these cases you have since you have not uniform composition of the solute in the solid case. So, you get the expressions for the Fs as Cl minus C naught from the equilibrium lever rule, and you get Cl minus Cs bar. So, that is known as the average composition of the solid, that is Cs. So, from here you get large many equations, but this basically is giving you the concept about the case where there is not solid, no solid diffusion is there in the solid, and you have the complete liquid diffusion, and we can have expressions for FL also. FL will be 1 minus Fs. So, you will have Tm minus TL divided by Tm minus T. So, that way also you are getting 1 by 1 minus K, because we are getting TL minus Tm by C naught is equal to ml, because we know the slope of the liquidus line, which is assumed straight line. So, in those cases you can have the different expressions for Fs, Fl, and all that can be found out. There is another case where you will have the no solid diffusion, and you have limited even the liquid diffusion. Now, in such cases what is happening that you will have the solute build up at the interface, and because here you will have again this is in this case you will have only limited liquid diffusion is there. So, again in these cases if you try to understand through the phase diagram. So, what will be happening again here. In this case you will have because here because of the no solid diffusion and limited liquid diffusion, you will have convection also is assumed negligible. So, you will have neither the solid nor the liquid of uniform composition, and so the solute which is rejected in this case when k is less than 1. Now, that will be piling up and form a solute rich boundary. So, solute rejected gets piled up and and forms a solute rich boundary. Boundary layer ahead of growth front. So, in this case the equilibrium will be existing only at the interface, because you will have limited liquid diffusion as well as there is no solid diffusion. So, what happens in these cases, you will have the at the interface you will have solute segregation occurring. So, in these cases if you look at the so you will see that if you have this as the solid which is formed. Now, in this case your at liquid you will have this way you have piling up. So, this region is known as the solute rich boundary layer. So, you will have liquid, this is solid, and this side you have liquid. So, from K C naught to C naught it will be reaching, and so if you look see the variation of the K C naught. So, for the solid part from K C naught to C naught it will reach, and for the liquid part C naught to C naught by K it will reach, and this way ultimately it will move, and in the end it will also be moving, and this will also be moving. So, this will be coming to C naught in this case for solid. So, basically this region is characterized by a region of this solute rich boundary layer region, and in these cases as the condition will be for the ds into T or dl into T. So, it will be quite lesser than the L square values. So, that way those will be the conditions, and initial this will be case of initial transients or so. So, these are basically the three cases, and again here you will have there is certain mathematical formulation for finding the steady state composition profile, and it has been shown that it will be Cl minus C naught by C naught by K minus C naught. It will be basically exponential raised to the power r by dl into z. So, in this case r is the growth rate, and you will have the z as the distance from the solid liquid interface. So, z will be 0 at so when z is 0 at that place your Cl minus C naught has the maximum value, that is C naught by K minus C naught. So, that is how you get these values, and you will have these are the initial transients, and you have the final transients in these cases. So, there are certain formulas by which you can have the computation of the CL and CS. So, that can be found. So, we will see these 3 different cases to understand the solidification mechanism, mode of solidification and associated phenomena which results into the different microstructure in the case of the solidification of alloys in our coming lecture. Thank you very much.